You're listening to Encyclopedia Podcastica, a podcast from the Silicon Valley skeptics. Prepare your mind.
Hi, my name is Hunter Perrin.
And I'm Matt.
And welcome to Encyclopedia Podcastica. This is our first episode.
All right.
Encyclopedia Podcastica is recorded in front of a live studio audience. Woo! There's
All
our
of
studio
us.
audience.
Yeah.
Our whole studio audience. Woo! You know, Matt,
Yes,
I've
Hunter.
been playing a lot of Pokemon Go recently.
Really? What's that? I've never heard of it before.
Shut up. I know you play.
No, that's true. That's true. What level are you? I'm level 23.
Oh, that's
still.
so cute.
Yeah.
I'm level 24.
Ooh, I bow before your pokiness.
That just shows I have devoted so much of my life to Pokemon Go.
Or spend a lot of money.
That too. Which I'm about to buy another one of the large.
Oh, you
Pokemon.
ran out of the
I'm
first
about
batch.
to. I can't even afford 200 Pokeballs anymore. That's how
Oh my
poor I
God.
am.
I just go to.
I need government-funded Poke support.
I mean, seriously, you have Meowths to feed.
That was so bad.
I had to work that one in. I've been saving that for so long.
Yeah, I'm glad we chose this topic for our first episode.
That's right.
So anyway, it's got me thinking, how does my phone know where I am?
It's magic.
It's not magic.
It's not
It's the
magic.
Global Positioning System.
Oh, is that what it stands for? GPS.
Yes.
I thought it was giant penis system.
That's a totally different system.
Totally different one. Okay.
That's
Next week.
that one.
That's
That
next-
one is Brazzers funded.
Okay. Of course.
We're talking about the government funded one.
Okay. Right. Government would not fund the other one, unfortunately.
Not publicly.
Not publicly.
I
Yeah.
hear you have an interesting story about.
Yes, actually, I have an interesting story that kind of covers the whole history. Not really the whole history, but some of the history. Anyways, I grew up in Florida, as you know, as now our audience knows. Woo! And
Yeah,
in
Florida.
Woo,
Yeah.
Florida! It's like the
Alligators.
best state and stuff.
and
And meth.
and hurricanes.
Hurricanes. So we do. There's a lot of stuff you do in Florida, as we know, but a big
Is there?
one.
I thought you just retired and died.
Well, there are beaches too, you know, and there's alligators.
Yeah,
got
you
gator
retire and you
wrestle.
die on the beach, and then you get washed into the ocean.
And you can buy an alligator, right? Yeah. It's a cycle of life. Anyways, no, I used to do a lot of fishing, specifically with my dad, right? So we would go into the Gulf of Mexico. So that's the West Coast. West Coast. Just making sure. Of Florida. And we were on my dad's boat. And we would actually, it's a big enough boat that you could actually go out so far that you could not see land.
In other words, it's a big enough boat that you could go out there and die.
Yes. If we didn't know where we were, we could die.
That is a very important thing to know.
Right. And realize when you're out on the ocean, right, there's no landmarks around. It just looks like water everywhere. And if you're far enough away that you can't see land at all. Like,
There are no landmarks, but are there watermarks?
There are no watermarks either.
There's just a big logo. Ocean.
You are...
I saw that on a map. I thought that was real. Isn't there just
It
a
said
big
ocean in the
Gulf of
middle?
Mexico?
Right. No, we actually didn't get all the
Where
way
are
up to
we?
the-
Oh, we're on the
the
G.
letters.
Okay, we're
Yeah.
good.
Right. Anyways, so see, this is back when I was a kid, back in the Stone Age, when we didn't actually have GPS when we were doing this and out there fishing. So we used the precursor to GPS. There were a couple of precursors.
Maps.
There were maps. So nautical maps, that was like a big one. But
Were there
it did-
nautical maps? Like, this is water.
Yeah, that was pretty much what it was.
If you go north, there's more water.
South, more water. East, more water. But then you hit some land, and then
There
there's
were
more
those
water.
sky maps.
Sky
Like, to
maps.
be honest, that's how people did it before any technology. They would look at. Well, I guess
no, I mean,
some
they had,
technology was required, but
yeah, it was
before
sextants,
anything electrical,
yeah,
they would look at the sky and
right,
see the
and just track
stars. And,
so we didn't
and
do
track
that.
themselves based on the movement
you know,
of the stars.
I'm an old guy.
That doesn't work in the
Wasn't
day,
that
by the
old.
way.
That's right. That's another issue. And you kind of track by sun during the day unless it's noon, and then it's like what the crap. Anyways, so we didn't do that. We actually used Loran. So you know what you've heard of Loran? You've heard of it? No, you have not.
I don't.
Okay.
No.
I think it's. I saw a couple of descriptions of what the name is, but it, basically long range navigation is what it stands for. And instead of like GPS, they were using satellites. Loran was big radio towers, basically, and it would triangulate. Is that the right word? Not triangulate.
Trilaterate.
Trilaterate. Ooh, we talked about this. Trilaterate.
Actually, I think Loran might. I don't know.
Do. Yeah.
I don't know.
Anyways, it was based on big radio towers that, since we were in the Gulf of Mexico, were along Florida's coast, right? And it worked decently well. I think you would go to where your GPS, your Loran coordinate would tell you to go, basically a lat long, right? And it wasn't perfectly accurate, so you were in like maybe a football field distance from where you're actually supposed to go. So you'd like, if you're in the boat, you'd just do like a spiral from when you get to the point you're supposed to be, and you do a spiral, and you're looking. And basically, since there's no landmarks, what are you looking for? You have a depth sounder, which we can go on talk about in a different podcast. But you're basically looking at what the bottom looks like under the water.
So you use the Roomba method of searching for something.
It was the Roomba method, exactly. Although usually my Roomba just goes in like one direction until it hits something and then turns. Is that an older version or something?
I don't know. Mine spirals.
Oh, your spirals? Okay.
Yeah.
Mine
until it hits something.
Okay. Well, in the ocean, it would just keep
or until its
spiraling
battery
and
runs out, and then it just makes this really sad noise.
It's like, feed me. The feed me beeps. Or
if it gets stuck, then it makes this like help I'm in peril noise, which is like actually distressing for me.
Yeah, I think I've heard that a few times. Yeah,
I think I'm attributing agency to my Roomba, which is dangerous. I shouldn't do that.
Yeah. Well, at least it's somewhat artificially
Lest I be
intelligent.
sad when my Roomba finally dies.
Right,
instead of just getting a new one.
Really, like a burial and all that stuff. And you really shouldn't bury batteries. That's a bad idea.
Roomba burial.
What would you just?
It was a very
dump it at
dirty
sea?
grave site because the Roomba.
The Roomba didn't work, so that was it. Anyways, coming back to my story, which you've
yes, you were spiraling around like a Roomba.
Distracted me from. So that's how you do it with Loran. Then this amazing new technology came out called GPS.
Well, hold on. Loran wasn't just for boats.
No, it wasn't just for boats.
It wasn't even designed originally for boats.
The only time I actually ever used it, or I was somewhat involved with using it, because at this time I was really, pretty young, so I wasn't actually driving. I wasn't old enough to drive a boat or anything, or a car. I don't think actually there's an age limit.
When it's a boat?
Pilot? Captain? It's not really captain, because that's the person in charge, so it's not necessarily the driver. Pilot, I guess, would be the correct name.
Pilot? Okay.
We can
pilot a boat.
We'll correct this in the next episode. Because this is really important to know on the GPS podcast, right?
If we got nothing wrong with this episode, then we wouldn't be talking about enough. So
right.
We're bound to get something wrong.
So I guess Loran was developed by the U.S. Was it the Air Force first? Or Navy, because I know it was eventually it was being run by the Navy, or at least those particular towers or something were being run by the Navy.
It was designed by the U.S.,
but it was basically the U.S. government. Yeah. We can talk about this in the history part, right?
The U.S. wasn't the only system like this. There was also GI, or G. I'm not sure.
Right.
I guess it depends on how you pronounce GIF.
Okay.
If you pronounce it like a heathen
Yeah.
and you say GIF,
Right.
then you would say G.
And then we'd kill you.
That's drastic. Holy
Well,
cow.
I mean, that's what you do with people, internet arguments. You just, gotta kill people sometimes. Anyways.
Kill you
So-
in an animated GIF. So yeah, Guy and Loran used the same method for
Same method. So it's
for
basically
locating you.
a bunch of radio towers, and we're figuring out the distance we are from. Your position is the distance you are from each tower.
But
It gets more complicated, right?
it
We're
it
gonna
would
talk about this.
it wouldn't just measure the distance from one, because it doesn't know basically when it wasn't able to synchronize with one, so it would use two of them and calculate the difference between the distance of both of them,
Okay.
and use that to create these long lines, parabolic lines,
Okay.
and then do that for several pairs of them, and where those lines intersect was where you were.
Okay. Good to know.
We'll
I
get
didn't know
more
that.
into this when we talk about GPS, because GPS can
Uses
work the
similar.
same way.
Yeah. So eventually we started using GPS. And I looked this up and I don't remember what it was called now. I should have written it down. But when GPS first came out for commercial use, originally it was just military use, just used by the military to find for people to know where they are. But eventually they let us civilians use it. And of course, boaters are going to be one of the first people to use it, because we really need a good way of determining where we are location-wise. We're trying to find a fish out in
This
in the
was
middle.
all leading up to Pokemon Go.
Yes, well, we're going to get to that. We're going to get to that. So, because it's really important that we have GPS for Pokemon Go. Now, we
The
didn't know it
military,
back in
the
day.
military from the 70s was thinking, how
Hey,
are we going to catch imaginary creatures? We're going to need some sort of satellite system.
That's right. How are we going to catch them all, really? Did you see the joke that back in my day, if we wanted to go around searching for imaginary creatures, we took LSD. Like real people. Anyways, GPS, when it was originally given out to allow civilians to use it, they did something to make it not very accurate. And right now I don't remember the name, what they called it. But basically, it wasn't allowed. Again, you were still in like the football field kind of area. You got close. You go where the coordinates said to go, and when you got there, if you weren't really there, you do the spiral out until you found really where you were, because you're probably within like a football field.
Yeah, that was called selective availability.
Selective availability.
Yep.
Yes.
Yeah,
Should
where
have,
the government made this very complicated system to let you precisely pinpoint where you were, and then purposefully introduced errors
Right.
for everyone else, not for them.
Not for them. They had was it actually the errors were introduced by the satellites, and then the U.S. government, anybody actually working in military, were able to reverse it?
Yes.
Or was it? Yeah. Okay.
Yeah, we'll talk about it.
Okay, we'll talk about that later. But I
how it
remember
works.
what eventually happened is after using GPS, the old version, GPS not very accurate with the selective availability for a period of time. Eventually, the military, the U.S. government decided that anybody who they're actually worried about getting the GPS and using it inappropriately probably have already figured out how to decrypt it, and so to speak, and get really accurate GPS. So they ended up turning that off completely. So now we have fairly accurate GPS. Is that correct? And I remember going.
Well, I think most of the reason was commercial, because it was starting to become much more used in commercial situations. Like
so it became more important. That
yeah,
it
became
more
much
accurate.
more important, and we wanted to basically make it useful, because it wasn't that useful when
Right.
selective availability was on. It
Right.
really was only useful for certain applications.
Right. So that made it really useful for fishermen now that we can go to our super secret fishing spot and go directly to it and not have to do this weird spiral thing. We know exactly where we are at any given point, and we know how to get back. So as long as we don't run out of gas or anything.
No more Roombaing the ocean.
No, yeah, I don't have to Roomba the ocean anymore. So that actually, GPS is strange technology or good technology for me. It keeps coming back in my life. So later, after I graduated from college, I'm not in Florida anymore. There's another part of the story I haven't told you yet.
You're not in Florida anymore?
No. This point in my story, I'm not in Florida now.
Just for the listeners, we're sitting in a room in California, so obviously you're not in Florida anymore.
Anyways, after Florida, after graduating from Florida, I moved up to Virginia and started working for a government contractor, which normally I wouldn't be able to tell you what I was doing with a government contractor. They're really kind of iffy about such things. But this particular...
But you've already eliminated all your assassans.
I've already eliminated... Yeah, exactly.
So now you can tell me.
I've already eliminated the government, so I don't have to worry about them anymore. No, I didn't eliminate any assassins. I was not working on any
Nobody's going to come after you if you tell me.
Super secret project at that time. Just saying. I worked on a project that tracked landmines in war-torn countries, so humanitarian efforts can go and clean them up. So it's not military breaching, right? That's where the military will try to clear a path through a minefield to get their troops across. This is for humanitarian reasons, cleaning up the entire minefield. So that when
the war's over, civilians don't go and accidentally step on those landmines.
Correct.
Which
Civilians
would be really bad.
And very importantly, like their cattle or other animals, but which like it's it's not as bad if animals are hurt in landmine explosions, but
still bad,
really
but
damaging to economies and such. So having GPS, as you can imagine, having very accurate GPS was really important in that area, that project. And so you wouldn't walk up to the edge of the minefield with your little cell phone GPS. Actually, at that time, it hadn't been moved into cell phones didn't have GPS yet. Right before that happened. So you had a separate external device that connected to, wasn't even a cell phone. It was actually like some other handheld, like not a Palm Pilot, but something similar to that.
A GPS receiver. A separate.
Something. Yeah, like it was a
have those.
It was a generic.
You can still get a GPS receiver that's not a cell phone.
It was a generic device, like almost like an iPod or something like that.
Oh, you mean the thing that it connected to?
It connected to, but it was a separate GPS device there. And you wouldn't like walk up to the edge of the minefield and like stick out your foot and be like, "Is there a mine here?" And this is a safe point. No, you wouldn't.
So it was like catching Pokemon, except when you threw a Pokeball, it would explode.
Yeah, pretty much. Yeah. No, what we would do is there would be some sort, in this case, a landmark nearby, and you'd put the GPS unit on that landmark or very close to that landmark, and you let it sit there for a while, because even though GPSs are more accurate now, they're still like a few feet inaccurate. There's like a few feet of error, right? I think at that time we were guessing like around 10 feet or something like that. I think it's more accurate now. But if you left the device in one position and let it record points and then average the points that it was getting, you ended up with a very accurate location. And you'd use that as a starting point. And then instead of using GPS at each edge or each point surrounding the minefield, you then pull out your laser rangefinder and then mark off the points of the minefield without getting close.
Actually, there's a system called differential GPS where you can use basically that same idea of getting one very accurate GPS receiver and using that to eliminate the errors of other GPS receivers that are moving nearby.
Right. And I've heard of that too before. We did not use that. And again, you can't.
That's a pretty expensive system.
Yeah, very expensive. The other thing is, again, you don't want to get close to the minefield, even if it's well marked. So the people who are marking it off were not allowed to actually go there. You would use the laser rangefinder for the close points to the minefield. So, and then after that, of course, we get, a few years later, we get Pokemon.
The real purpose.
The real reason for GPS. So Hunter, tell me, how does this GPS thing work?
It is amazing. It is a huge technical feat of engineering how this, not only the system works, but how we overcame all of the things that were trying to keep it from working. So GPS, as of right now, is a constellation, right now being July 2016, is a constellation of 31 satellites.
Wow.
It needs 24 to work, but right now we have some extras. So having 24 gives you line of sight access to 4 satellites wherever you are on Earth, which is what you need.
Assuming
you need
there's nothing
4
overhead
satellites.
of us.
Well, yeah. I mean, if you're standing underneath
if you're
a couple
inside
skyscrapers, then
in a room talking on microphones,
then you don't have line of sight of anything in the sky.
Right.
So
there are other
not
tricks
even
that are used,
the sun, which
yes,
you shouldn't be staring at the sun anyway.
Right.
So we put all these satellites in the sky so that you could see 4 of them wherever you are, but they have to be in a very specific orbit to do that.
What kind of orbit? It's not geosynchronous orbit.
It is not a geosynchronous
which is
orbit.
What I thought it might be, but
it's
I
not. They do
sure.
actually move relative to you. So if they orbit the Earth about once a day, I believe. Could be twice a day. Anyway, they move at 3.87 kilometers per second.
Wow.
Which is
That
14,000 kilometers per hour.
How many miles per hour is that, since we're in the U.S. and we don't understand
know.
kilometers? Maybe we could use this thing called Google and...
Yeah. That would be 8.7 thousand miles per hour.
Wow.
Which is really fast.
Right.
So they need to be that fast in order to orbit where they are. They're 20,200 kilometers high, which again I don't know what that is in miles. Let me look that up. Probably should have done this before
really,
recording.
Really
that's
far away.
That's 12,500 miles up.
Wow.
Which is really high. That's 5.3% of the distance to the moon. So,
which means the moon's really far away.
The moon is very far away.
That's what I'm getting out of this.
Much further than the satellites. But still, we are 0% of the way to the moon.
Right.
So take what you will. Anyway, it's not geostationary. Right. They are moving relative to us. I had it written down. Their orbital period is about 12 hours. So they orbit the Earth twice a day.
Okay.
So we put all these satellites up to give us a way to calculate where we are.
So hold on. When you say we
humans.
Who? Humans.
But specifically the U.S.
Okay. The U.S.
Specifically
government.
the U.S. military and very specifically the Air Force. Okay. The Air Force owns all these satellites.
Right.
And they provide access to them for free to civilians.
Well, they can't really block it, right? Because they
could block it, absolutely.
Out. Oh, I thought they
could totally block it.
Okay.
No, they have encrypted channels that they use, and then they have unencrypted channels that we use. Okay. If they want to, they could just turn off GPS for everyone but them.
Which is why countries or like Europe is setting up their own.
Yes, and Russia has their own.
Russia has their own. Does China have their own? They don't have their own.
I don't know.
Oh, okay.
But Russia definitely has their own already.
Okay.
And then Europe is sending up their own satellites. They're not GPS, but they're the same thing.
The same technology.
GPS is actually like a name for our system.
Right.
Yeah. So the way that you calculate your position from these satellites, there's actually 2 methods that you can use. The first method is the one that is easier, but you need a very accurate clock, which our phones have. Our phones have a...
Really? Doesn't seem like it's very accurate. I don't know.
It is. I mean, it's not extremely accurate. It's certainly not as accurate as the clocks that the satellites have.
They have
but it's accurate enough that we can calculate...
Is there like an atomic clock in our phone?
No.
Okay.
But there is an atomic clock in the GPS satellites.
Oh.
So
Yes.
we can use them to basically have atomic accuracy clocks.
Okay.
So we have quartz clocks in our phones, which
Right.
are different than atomic clocks. They use a quartz crystal.
Right. Just like the
to-
old watches that
Yeah, just like your
before
watches.
they became smart.
They still have quartz clocks
Oh,
in them.
okay.
Smartness does not preclude quartz.
Ness.
Is that the right word? Preclude? Whatever.
Whatever.
So our phones have a quartz clock, but it's not as accurate as the clocks on the satellites. But we need a really accurate clock to calculate our position from the satellites. So the way it does this, well, first of all, the way it calculates the position from the satellites is a method called trilateration.
Okay.
So trilateration will take 3 measurements from 3 satellites. So for the first satellite, what your phone does is listen for the signal from the satellite. And once it finds it, it gets from that signal the time, which is weird that that's basically all you need, the time, and also you need the position of the satellite. So it will send that as well. So your phone receives the time and the position of that satellite, and from that it can calculate how far away that satellite is from you.
Okay.
And the way it does this is it uses the speed of light. Because these signals travel at the speed of light.
Really?
They are light.
that-
I mean, radio is light. I mean, it's an electromagnetic radiation coming from the satellite. So your phone will listen to this
I thought it was like just sound, like the satellite just screaming, as it's going across. Why did you put me up here?
It's so cold.
In a way, it is. It's just screaming with light.
Oh, okay. And
It
the
sounds way
time,
slower.
it's like, I've been up here so long.
So it sends out the time that it sent the signal.
Okay.
So let's say we're standing on a baseball field,
Okay.
and you want to know how far away I am from you.
Okay.
So I take a baseball, and I look at my watch, and I write down 12 o'clock and 0 seconds and 0 hundredths of a second. And then I throw my baseball at you at that time. As
Okay.
soon as that time hits, I throw my baseball at you.
Okay.
And my
So
baseball travels at 20 meters per second to you.
Okay.
I can't actually throw a ball that fast, but
I have no
for the
idea
sake
how
of this
fast
thought
it is.
experiment,
Okay.
let's say I'm decent at baseball.
All right. So you throw
So
the ball
I
at
throw
the
my
speed
ball
of
at you.
light. Because we're talking about light.
I throw the ball at
right?
the speed of light. Everything explodes. The city is
Right.
destroyed. So I throw my ball at you at 20 meters per
And then-
second.
And then the Yankees
Half a second
hire you as a
later-
pitcher.
You catch the ball. You
Okay.
don't know what time I threw the ball, but you catch the ball and you look at your watch and you see that your watch says 12 o'clock and 0 seconds and 50 hundredths of a second.
Okay.
So the ball took half a second. Once you look at the ball and see that the time the ball says was half a second earlier, you can use the speed that the ball was traveling, 20 meters per second, to determine that the ball traveled for 10 meters
Okay.
because it traveled half a second at 20 meters per second.
Oh, yeah.
So now you know that I am somewhere on a circle that is 10 meters away from you.
Right. So, but I have to have an accurate clock
You
to
do.
know the difference.
Both of our clocks have to be in sync
Okay.
to
Like the band.
in order to be able to do this.
Not like the band.
Tear my heart away.
I don't know any NSYNC songs, so I couldn't.
That
Bye,
might- that
bye,
might-
bye, bye.
Okay.
That's the only one I
I
know.
mixed them up with 98 Degrees. I don't know.
I mix them up with Backstreet Boys, so
Yeah.
it's all right.
Right.
They're all the same thing in my mind. So anyway, we have this this time signal from the satellite that your phone
Okay.
received.
Right.
So it knows what time that signal left the satellite, and it knows at what speed that signal was traveling to reach you. It was the speed of light.
Right.
Which is
You can look up that.
300,000 kilometers per second, roughly,
Ah.
or 186,000 miles per second.
Okay. There we go.
Since we're in America, and for some reason we still use miles.
That's right.
USA.
So our phone can say that signal traveled some X amount of distance to get to us, just using the speed of light and the time that signal left.
Okay.
So with that information and the information that it knows where the satellite is, it can create this big sphere, imaginary sphere out in space where we are located. I mean, it's out in space, but it also...
That's not where we're located.
It's where we
could
be. We are somewhere on the surface of this sphere.
Right. Okay.
And of course, our phone assumes that we're somewhere on the surface of the Earth.
Okay.
So it's
Which
got
is
another
sphere.
sphere.
Okay.
Yes, it's got another sphere
So-
that it can intersect
intersection of
with
two-
that other big sphere.
So the intersection of two spheres
Is a big circle.
is a big circle. So you're somewhere on that circle.
We are somewhere on this giant circle on Earth. And that circle is probably thousands of kilometers wide.
Miles?
Or
thousands of miles. This is
or miles.
We're specific. Okay.
And we're somewhere on that circle.
Right.
But it doesn't know where on the circle we are. So it's got to ask another satellite. Not ask, but it's got to detect the signal from another satellite and do the same thing to build another big sphere from that satellite.
I think the satellites are kind of lonely up there. It'd be nice if we asked them once in a while. And,
Oh, they're not lonely. They got
just-
31 of them up
Oh,
there
yeah,
having
that's
a
true.
party. It's a GPS party
big
up there.
space party.
It's a satellite party.
Satellite
Ain't no
party.
party like a satellite party. Because the satellite party doesn't stop until something goes drastically wrong.
Right. Like
And then
Space
all
Lab
satellite
falling from the
parties
sky.
stop.
Don't stop until a solar flare?
They can
No,
survive a
okay.
solar flare. A coronal mass ejection is probably...
At the right direction.
well, depending on how big it is, might wipe them out.
Oh, okay.
But it would have to be an enormous coronal mass ejection directed almost
direction.
perfectly at us
Yeah.
to actually take out satellites.
Okay.
But anyway,
Anyways.
that's off topic. So it does this for a second satellite. It makes this second big sphere.
Okay.
And now we have three big spheres. The big sphere from the first satellite, the big sphere from the second satellite, and the big sphere of the surface of the Earth.
Okay. So,
They all intersect at 2 points. If you take
Right.
three big spheres
so
and you
end up with two circles that are intersecting
yes,
and two circles that intersect and will intersect at 2 points.
2 points. Yeah. So
Right.
if you can imagine the Earth and you draw a big circle on the Earth and then draw another big circle on the Earth, a little further away, but they intersect. There's these 2 points that they intersect, and those points could be thousands of kilometers or miles away from each other.
Okay.
So it's got to do this a third time. So it does the same thing with this other satellite. And now it's got 3 big spheres plus the Earth. And that eliminates that second point, because you have 3 big spheres and the Earth all intersecting. They intersect at 1 point.
Ah.
So now it knows you are at this point,
Okay.
but not quite.
So that's 3. We have 3 satellites now.
3 satellites so far that we've been using.
Okay.
So
And we have a point.
we have a point,
But
but your phone's clock is not as accurate as the clocks on the satellites.
right.
So you
'Cause
can
it's quartz.
almost guarantee that your phone's clock is going to be at least several microseconds off, if not milliseconds, which it means the difference between being, a couple meters accurate versus being hundreds of
Miles.
kilometers accurate.
Miles.
So your phone needs to do this for another satellite, basically.
Okay.
So you do the same thing for a fourth satellite, and you're going to get it to intersect, but it's not going to intersect in the same point as all the other ones. It's going to be off.
Okay.
So now your phone takes all these, and it applies a clock bias factor. Basically, it subtracts an amount from what your clock says and kind of tries to make these 4 spheres intersect at one point. So it's adjusting your clock to adjust the distance to the satellite that it's calculating. And at some point, it's going to find the right adjustment so that all 4 of those spheres intersect at one point. And then it knows how far off your clock is from the actual time that the GPS satellites know.
Okay.
So you can use this method to determine your clock's bias.
Okay.
And that lets you figure out not only where you are, but what time it is. Which, that's another application you can have for GPS. GPS doesn't only tell you what location you're at, it also tells you what time it is. Pretty much perfectly. I mean, there's atomic clocks on these things, which is the most accurate clocks humans have ever devised.
Right. So there's a certain period of time in which they are accurate, right?
I'll get to that.
Okay. I'm jumping ahead.
Yes.
So for your phone, it's like a millisecond. It's accurate, and then it's off.
Yeah, for your phone,
but it's really
going to be off pretty quickly.
Right, but you're not going to notice until
it can use GPS to determine how far it's becoming off, and then it can adjust based on that. And that lets you keep track of where you are, so you can drive, and it knows where you are while you're driving or catching Pokemon.
Which is important.
Yeah.
Yeah.
Hopefully not the 2 at the same time.
Yes.
Please
not
don't drive
Pokemon
and catch Pokemon.
Drive. Pokemon and drive. Pokedrive.
Don't make that a word.
Oh.
Now it's a thing.
Oh, no.
Send out a tweet.
So that is the first method that you can use for GPS. That does mean you have to have a somewhat accurate clock.
Right.
If you don't have access to a somewhat accurate clock, you can use a different method called
inaccurate clock.
called multilateration. So there's trilateration, which is the method where you build these big spheres in space and then they all intersect at one point. There's multilateration, which is where you build these big hyperboloids in space.
Okay.
So if you don't know what a hyperboloid is...
I didn't think we were building these things in space, but...
You know what I mean. You're calculating.
Calculating. Okay.
Calculating imaginary ones in space.
All right.
So if you don't know what hyperboloid is, it's this figure that is...
So
if you imagine 2 cones... Hyperboloid. If you imagine 2 cones pointed at each other, and then you smush them together so that it creates this kind of like curved surface between them... like if you have a big tube and you squeeze it, it's going to curve down into this section and then go back up. A hyperboloid is like that, except it goes off into infinity. So the 2 ends expand into infinity.
Right.
So the way it builds this hyperboloid is it does this calculation, this sphere calculation kind of for 2 satellites. And then it measures the difference between them. So you don't actually care about your clock bias. It doesn't matter what your clock bias is. If your clock were off 100 years, you could still do this. You'd have 100 years and 1 millisecond, and then your other one would be 100 years and a half millisecond, and then you'd have your range as half a millisecond.
Okay.
Which actually would be like an enormous amount of distance, because this is light we're talking about. So... you use this this method to get the range difference between 2 satellites. And you need at least 3 of these range differences to build 3 hyperboloids out in space. To
calculate
3 hyperboloids out in space. So what the hyperboloid is where you are relative to those 2 satellites. So those 2 satellites are going to appear in the big conical sections of the hyperboloids, and you're going to be somewhere on the surface of that hyperboloid. And what it's saying is basically, this satellite is X amount of kilometers further away from me than this satellite. And there are an infinite number of points in space where that could be true. But you're going to assume that you're nearby those satellites. You're probably not going to be calculating your distance calculating your location with GPS if you're near like Jupiter. You'd probably use a Jovian positioning system, which would be very different.
Yes, yeah. Or the stars, just no.
Yeah, probably
no, you'd
stars.
probably, be dead because Jupiter is so big and its gravitation so strong, it would just crush you. And then
the radiation would probably kill you before
that's
the
true.
Gravity would.
Yeah, that's a good point. Yeah.
Yeah.
Anyways,
Jupiter is actually like bathed in radiation.
No, it gives off its own radiation, right?
Yeah, that's what I mean.
Yeah.
It's around Jupiter is this enormous belt of radiation that we can't even fly satellites through it because it will kill our satellites.
Why? Why would it kill satellites? But where's the radiation coming from?
From the motion of things inside Jupiter. Okay. Jupiter, like our sun, the same thing, is bathed in this radiation, and to a certain extent, Earth is as well. But it's so very small that it's not going to kill us. But anyway, that's besides the point.
Anyways,
so
back to Earth.
Back to yes, back to this multilateration. So we build these we calculate these hyperboloids.
So I don't know what the intersection of hyperboloids are.
You'll get a curve. So the intersection of two hyperboloids, you'll get this big curve.
Okay.
I mean, obviously depends on where you are, but usually
it's not
if you're about the same distance from these two satellites, you'll get this curve section.
So is this curve like a parabola curve or not really?
I'm not sure, actually.
Okay.
I think it's shaped like a parabola.
Okay.
But yeah, once you intersect it again, and again a third time. No, wait. Once you intersect it again, you'll get a point. So you have three hyperboloids intersecting. You'll get this point, along with the Earth, because it uses a
point that's hopefully on Earth.
Yes. So actually, you can use GPS to determine your location in space.
Right.
But you have to consider multiple points a lot more than you do on Earth, because you can't assume that you're on the surface of this big sphere that is the Earth.
Right.
So,
if you went back to the spheres thing, it actually still works out because you have intersections of multiple spheres. If you drop Earth, you still have it.
Yeah, but you'd have to have more satellites
to be accurate.
Yeah.
Yeah. Because you don't have this additional sphere that can rule out points that are out in space.
Okay.
So this method also requires 4 satellites because you need 3 range differences, but it doesn't depend on your clock bias.
Okay.
So,
right.
But again, all of these methods, trilateration and multilateration, all depend on the speed of light and the accuracy of the clocks in the GPS satellites.
So I got a couple questions there.
Okay.
First, speed of light. We don't have any problems with it changing a little bit, moving through different...
We do.
Okay.
Yeah, so I'll get to that.
Yeah, and the other one is, we mentioned it before, but the accuracy of the clocks.
Yes. So the accuracy of the atomic clocks, they are extremely accurate.
They're so
but
accurate.
They are. They will be off by less than a second over millions of years.
Wow.
But just because the clocks are accurate doesn't mean that time itself is accurate. Which is a really weird thing to say, but it totally matters in this situation.
Yes.
So way back when Einstein was developing his theory of relativity, his theories of special and general relativity, he described 2 very specific effects. In special relativity, he described a time dilation effect where the faster something is moving relative to you, the slower you will measure its clock.
Okay. So the satellites are moving really fast.
They are. They're moving 3.87 kilometers per second. super fast. I'm not going to calculate that to miles again.
Oh, okay.
We did it earlier. I don't
You
care.
didn't write it down. Okay. But so a lot of
America
miles
needs to use kilometers anyway.
Okay.
Anyway, these satellites are moving very, very fast, especially compared to us on Earth, because the fastest we can go is like in a plane if you're going like 700 miles an hour, roughly, if you're going really fast.
Right.
In a commercial jet, you won't even get up to that. You'll get up to maybe 500 miles per hour.
Right.
So you're basically standing still compared to these satellites.
Right.
So the clocks on the satellites will run slower due to this effect. They will run actually approximately 7 microseconds slower.
Ooh. So wait.
Per day than a clock here on Earth.
So we know about milliseconds is thousandth of a second. Microseconds
is a millionth of a second.
A millionth of a second. So it's
1 millionth of a second.
It's a really tiny
so
measure.
if you go 1/1000 in that second,
right,
there were 1 million microseconds.
Whoa. So it's a very tiny change. But
it's a tiny change, but you're dealing with the speed of light, which is 300,000 kilometers per second.
Right. So that could be a big deal.
So 300,000 and 1 million aren't actually that far off.
Right.
So you could be off by
it's like a third.
You could be off by kilometers every day if these clocks were running without any account for special relativity.
We're not off by
We're not.
kilometers because we can catch the Pokemon that are right next to us. This is really important.
Yes, we're not. So you have to take into account that 7 microsecond drift per day. But it's not just that. It's not just the slower clocks because of special relativity. We also have general relativity, which showed us that the further you are away from a big gravitational source like the Earth, the faster your clock will run. So a clock down here on Earth will run a lot slower than a clock up in space. And the satellites are in space. So their clocks will actually run 45 microseconds faster per day due to them being so far away from the Earth. So if you ran an atomic clock here on Earth and you had one out in space, you started them at exactly the same time, ran them for 1 day, the clock in space would be 45 microseconds faster than the clock here on Earth after that 1 day.
Assuming they're the same distance as these GPS satellites are and all that.
Yeah.
Okay.
Yeah.
Gotta be specific.
Assuming they're 20,200 kilometers away and also not moving. If they're moving, then you also have that 7 microseconds slower, which the GPS satellites are. They are moving and they are far away from Earth. So you have the 7 microseconds slower and 45 microseconds faster, which means if you combine the two,
we have to do this high-level subtraction.
Indeed. This is very, very complicated math.
Right.
It's 45 minus 7, which is just a crazy calculation, but it ends up with 38.
38. So
Thank you. Thank you. That took all of my first grade math skills.
Right.
All of them. So you end up with 38 microseconds of drift per day. That the GPS clocks are going to be faster than a clock here on Earth, including the clock in your phone.
All right.
I mean, the clock in your phone is going to be off by more than that because it's a quartz clock and not an atomic clock. But if you were running an atomic clock in your phone...
which would be like a really big phone that you really couldn't fit in your pocket.
Probably, yeah.
But you could really find those Pokemon, though.
Indeed.
Yes.
Catch them with atomic accuracy. So you have these clocks in space that are running 38 microseconds faster than the clocks on Earth. So we needed to take that into account. So before we launched these satellites into space, we adjusted their clocks to just run 38 microseconds slower.
Okay, and that solved all problems, and we're good. Okay.
So if you took one of the GPS satellites, brought it back down to Earth, and just sat it
it'd be totally useless, but it'd also be...
And you had a regular atomic clock next to you on the other side, at the end of one day, the GPS satellite would be 38 seconds slower than the atomic clock.
Okay.
And that's on purpose.
Okay, so it just
because of these effects. 38
continuously-
microseconds, I mean. Did I say seconds? Certainly
I
not
think you did
seconds.
That'd be a lot.
4.
But microseconds. Okay.
Yes.
So how accurate...
I was only off by a factor of 1 million.
So how accurate do we need the clock to be for GPS? You have to have it really accurate.
You do.
Yeah.
You actually have to have it 25 nanoseconds
Okay,
accurate.
wait a second. What does nano
10 to the
mean?
9.
Nanosecond.
A nanosecond is a billionth of a
Wow.
second. 1
1
billionth
billion.
of a second. Which is crazy to think that in 1 second, there are 1 billion nanoseconds, and we need to be 25 of those accurate.
Wow. That doesn't even
25
seem... That
nanoseconds
doesn't even
accuracy.
seem possible. But it is.
So if we were off by these relativistic effects, if we were off that 37 microseconds per day, just FYI, our phones would be off by 10 kilometers per day.
Wow.
So you take
not
a
good.
phone, after 3 days it's off 30 kilometers. After, a year, it's off by...
And pretty soon you're catching Pokemon in the middle of the Pacific.
Pretty soon you're catching Pokemon on the moon, which you'd probably catch Mew.
Which would be weird because
would
you'd
be
be going
awesome.
up.
Yes.
Oh, yeah. Okay, fair.
I wonder if
Is
they
there a
did
Mew
that.
on
I
the
wonder
moon?
if they actually put Pokemon on like celestial bodies so that like I was actually wondering
Astronauts can go
the
there.
astronauts in the ISS. I wonder if they can catch different Pokemon.
Than
If
us?
they can catch like Mews and Mewtwo's
God, I
and
hope
the
so.
legendary bird Pokemon, that would be so
That
cool.
would be pretty cool.
I heard that at Fukushima, I think the site of radiation, that someone went there, and because they went there, their phone was connected to a satellite, and then for Pokemon Go, it started to generate Pokemon there, which is why other people went in there to find more Pokemon.
That sounds
Oh,
like
no.
a terrible idea.
Right?
Although I did read up or watch some documentary on it. You can get kind of close, like inside the area that you're supposed to be blocked off, and the radiation's not bad. It's not until you get actually to the site that it's okay.
Yeah.
But that being said, don't catch
Still
Pokemon in
wouldn't wanna go
radiated areas.
Don't catch radioactive Pokemon.
No.
Oh god.
But that's how you evolve them. No. Or
The radioactive.
metamorphosize.
Are the candies radioactive? I didn't know that.
Yeah.
You're just feeding
All
them
I
sources
know
of
is
radiation
that
and they mutate.
Pokemon candy
Evolve.
is made from Pokemon.
I've read that too.
Yeah.
That is not canon.
Pokemon candy is Pokemon.
That is not canon. That has not been confirmed.
You know what I was going for.
yes.
You know what you mean?
Soylent Pokemon.
Soylent Pokemon.
Okay, getting back on track.
Okay. That Pokemon
So-
was the track. Anyway.
So you don't just need to know very accurate time. You also need to know where the satellites are. So the satellites will be broadcasting what's called an almanac, which is
Satellite Almanac.
yeah,
Okay.
which is basically
That was
their
not very
location.
funny. Okay.
So they're going to be broadcasting their own location along with
so,
the time.
So how do they know where they are?
They know where they are by the military, basically. The Air Force monitors them and updates them with their own location.
Okay. So they don't use GPS.
They don't, surprisingly.
Okay.
The military uses radar to determine where they are and
Okay.
will update their location. So the way you get this information, the almanac and the time, is through this pseudo-random code, or PRC, that these satellites are sending out. There are two types of pseudo-random codes. Well, there's a lot of different types because each satellite sends out its own unique pseudo-random code so that they can all broadcast on the same frequency without jamming each other.
Okay.
So you'll pick up the pseudo-random code for each satellite on this frequency, and there's two different frequencies that they use. One is called a CA, or course acquisition code. That's course like rough.
Not as in the direction they're going.
Correct.
Okay.
Yeah, so this course acquisition code is what we use, what our phones use. It is the civilian GPS.
Okay, that was the one that they were messing with.
Yes,
before.
exactly.
Okay.
So then there's a different code called a P code, or sometimes it's encrypted, and when it's encrypted, it's called a Y code that the military will use.
Okay, it seems like it would have been E code for encrypted or something.
I don't know why it's Y code.
Yeah.
Why?
Y code.
Why code?
Why?
Ding.
Insert laugh track here.
We need a gong for this show. So whenever it tells a really bad joke, and hit the gong.
Wasn't that already a thing?
Well, I think it was a whole performance, a gong show, like a
Yeah.
Kathy Friscotti has a gong show every month. in San
Oh,
Jose.
really?
You do stand up, and if they don't like it, then
Then they gong you.
So this pseudo-random code is actually really useful for eliminating background noise because it allows you to amplify the signal using this really clever signal processing. So you have this pseudo-random code, and your phone also has the same pseudo-random code that it can check for through all this noise. And once it matches the satellite pseudorandom code with its pseudorandom code, it knows what to amplify or what to eliminate as the noise.
Okay.
So this pseudorandom code lets your phone read the information from the satellites, even though the satellites are basically broadcasting the equivalent strength of a 40-watt light bulb.
Wow.
Yeah, so imagine how little power they're broadcasting, and your phone can pick that up.
It's amazing.
Your phone can pick that up
at the same
from
time.
20,000 kilometers away.
Huh.
Wow. Technology is amazing.
Awesome. It is.
And what do we do with it?
We
play
catch
Pokemon.
So all of this is not immune to errors. There are a lot of errors. There are a lot of sources of error in the GPS system, and there are a lot of ways that we get around this error. First of all, we're talking about the speed of light, but
There's error in the speed of light.
kind of.
Okay.
So the speed of light is constant in a vacuum.
Right.
But these signals aren't just
So
traveling through a
space is
vacuum.
mostly a vacuum.
Space is pretty much a vacuum.
Yeah.
But the atmosphere is not a vacuum. It is decidedly not a vacuum.
that's good,
If it were,
'cause
we would die.
Yeah, I mean, I could breathe, so
Yes.
it's good.
So these signals are traveling through space.
Yes. And atmosphere.
But they enter the atmosphere, yeah.
Okay.
They enter the ionosphere, which is the big top part of the atmosphere,
Right.
which is a huge source of error for these clock signals.
That's where we keep all our ions.
That's true, actually. Well, we don't keep them, but
Okay.
it's where the Earth keeps
its ions.
a lot
Okay.
of its ions.
Yes.
We do have ions down here, too.
Okay.
We need them to live.
Yeah.
But the satellites will keep this model of the ionosphere and broadcast that model down to your phone or down to whatever is receiving their signal. And this model will let your phone or whatever receiver update its own calculations to figure out how to eliminate these errors from the ionosphere.
Okay. So I got a quick question about, and I assume it has something to do with this model, but is it the ionosphere, the one that moves the day and the night? You know what No.
I don't know.
Okay.
I have
To
not
double
heard
check
of
that.
I don't know.
There's one of them that when it's bombarded with, the sun's radiation, is pushed down lower.
Huh.
I thought it was.
It might be the ionosphere. I don't know.
We'll have to correct that in the next podcast.
Yep.
Okay.
But the receiver also needs to take into account what angle the signal entered the ionosphere, because depending on if the satellite is right overhead, it's going to pass through not a lot of ionosphere. But if it's over near the horizon, it's going to pass through a ton of ionosphere before it gets to you.
Right.
So your phone needs to calculate what angle this signal is getting to you through the ionosphere so that it can update its model. Okay. Or not update its model, but use its model to figure out what error this ionosphere is introducing. So there isn't just the ionosphere. There's also the troposphere, which is where all the weather happens.
Okay.
Which that is a relatively small source of error compared to the ionosphere. So your phone can basically assume that it's under normal conditions.
Okay. So like with the troposphere, are you having errors with like weather, or is it just
no?
It's
just the troposphere. Air. The errors are introduced by
has to go through a bunch of air.
Basically water vapor. So I guess actually weather.
That would be weather.
Yeah. That is weather.
So does it have like, a weather map going on in your GPS? Like it's being updated, or is it just not that? Is it just
it's not that complicated.
Okay.
You can have a really expensive GPS
that takes
system
into account.
that will take that into account. But no, your phone doesn't.
Right.
So you have the ionosphere and the troposphere, and you also have multipath errors. So multipath errors happen when your phone receives multiple of the same signal.
How would that happen?
That's a good question. Let's say you're standing next to this big skyscraper.
Okay.
So your phone receives two signals that are duplicates of each other. One signal you get direct.
Okay.
One signal just comes straight from the satellite to you. Another signal is the same signal but reflected off of the big skyscraper that you're standing next to and into your phone. So just like you can see a reflection of the sun and the sun itself, your phone can see a reflection of the satellite signal and the signal itself. So
that's why, like, if you're in a field or out on the ocean, you have much more accuracy.
It's much more accurate
than if you're in the city.
Surrounded by
I've
all
had
these
trouble,
buildings.
like being in, driving around a big city, and my car GPS starts having trouble and not quite getting me on the right road.
So that's probably due to these multipath errors.
Okay.
But phones are pretty good, or receivers are pretty good at using some signal processing to make sure that they only consider the first instance of the signal that they get.
Okay.
So,
because it seems like all the reflection ones would be the slower ones.
Take longer.
Yes.
They would take longer all the time. So you could potentially just throw those out.
Yes. So they do. They use some clever signal processing to filter out those extra ones.
Okay.
So multipath is not that big of a source of errors. It's actually a bigger source of errors than the troposphere.
Okay.
But it's not definitely not as big as the ionosphere, which is the biggest source of errors.
Ions.
Then there are ephemeris errors, which are errors that the satellites themselves cause. Basically orbital path errors.
It's not like somebody like put an error, like bug in their code on the satellites and cause it. No, it's just
no. They're errors basically caused by things like the moon's gravity, the sun's gravity, and the solar radiation on the satellites.
Okay. So every time I think of like errors and stuff, I'm thinking, since I'm a software developer, it's software. Because it's always software.
Nope, it's not software this time.
Wow.
It's just
unless it's like the Cosmos software.
We are all in a computer.
It's all a simulation.
Just the physics of us and stuff. So the almanac that your phone receives from the satellites includes information about this ephemeris errors. So the military will update the satellites with information about these ephemeris errors.
So the military is always in contact with these satellites and like sending information.
Usually, yeah.
Yeah.
So then I lied. Ionosphere errors aren't the biggest source of errors. They're the biggest source of errors now. But when GPS first came out to the public, The biggest source of errors was selective availability.
Coming back to that one.
Yep. Selective availability is an on-purpose error. It is meant to be there.
So is that an error if it's on purpose? Yes.
Yeah.
Because it's not accident. It's difference.
Yeah. It's a purposeful error.
Yeah.
So
Systemic
the military would include these timing errors into the satellite's data, and they could decode them.
Okay. So when it was a timing error, it was just basically reporting the wrong time, like off by a few nanoseconds?
Just reporting wrong information. So yeah.
Or position.
I think it would be time.
Was it time or position?
I think it was time.
Okay.
I'm not sure, actually.
So the satellite's like, I told him it was 12.
They're snickering at each other.
But it's not.
Damn it, Wheatley.
So selective availability was a problem when GPS came out, but it was turned off on May 1st, 2000.
Okay.
So part of the presidential decision directive goals for GPS in 1996 was to discontinue selective availability by 2006.
So what president was that?
That was President Clinton.
Okay.
President Bill Clinton.
Basically
He said, in order to make
End of his
GPS more useful for the public, we should turn off selective availability.
So
and
we
he
can
said we're
think-
going to do that by 2006, and they did it in 2000, 6 years ahead of schedule.
So you can thank Bill Clinton for playing with your Pokemon.
You can thank many people, including Bill Clinton.
Okay.
So these errors, they will account for the various different types of errors, account for a different level of errors. And the typical error in meters per satellite, the typical error in meters, all these different types are the satellite clocks introduce about 1.5 meters of error. Orbital errors introduce about 2.5 meters of error. The ionosphere introduces about 5 meters of error. So it's definitely the biggest source of error. The troposphere introduces about 0.5 meter of error. The noise around the receiver will introduce about 0.3 of a meter of error. And the multipath errors will introduce about 0.6 of a meter of error.
Okay. So do we add that all up and have our accuracy?
I haven't added them. You can add them. It's probably around 10 meters,
10 meters
of error. Yeah. Roughly.
I think that's what but the accuracy GPS is supposed to be.
So yeah, all of those errors will cause your location fix to not be perfect. You can't make a perfect GPS system. The universe is just not going to let you do it.
Even
and
after
neither will the
we,
military.
After
or
we
I guess they
correct
do now.
for all of those errors.
You can correct for all of those using a system
point.
called differential GPS, which we touched on earlier.
Yeah.
Where basically you have one stationary system constantly monitoring its position and detecting how much of an error there is. And then you have one moving GPS receiver that's nearby that will communicate with the stationary one and tell it, like, this is how much error you need to correct by.
Okay.
And that will make GPS of the moving receiver much more accurate. But it's also a very expensive system because you need this.
Right. So then at that point, we're talking about like centimeters.
Yeah.
Yeah.
At that point,
I'm not sure about this, but I am going to bring it up. I think some surveyors use that because they'll put one, a very accurate one, and then measure off that one with the other ones.
I believe so. Yeah.
Yeah.
So you'll get errors that are like within an arm's distance of the true location.
Seems like you'd want better for surveying, but okay.
Well, there are other methods that they could use.
Yeah.
To eliminate even those errors.
Right.
So one cool thing, or I guess not a cool thing, but one interesting thing about GPS is those time signals that they send out. Unlike a computer, which will use an epoch, which is just the number of seconds or microseconds since some time,
Right.
some arbitrary time, which in Unix computers is January 1st, 1970, Greenwich
Right.
Mean Time.
But we kind of do that too, although not at microseconds. It's, beginning year zero, right?
But in GPS, it's actually week based,
Okay.
which is weird. So you'll get a week number and then an epoch from the start of that week.
Okay. So it's
Which is very
so they're
odd.
basically counting from Mondays. They
Yeah.
okay, or counting the time since Friday or something till
Since
next
the beginning
Friday.
of that GPS week.
Right.
But one other interesting thing is GPS satellites aren't updated with leap seconds like UTC is.
Okay.
So your phone actually has to take into account leap seconds. So its clock is updated with leap seconds,
Okay.
but the GPS clocks aren't.
You want to describe leap seconds?
Leap seconds are used to make the standard time, which is called UTC, more accurate. They're basically seconds that are injected into our time, just like leap days are during a leap year. But they're just a single second injected in order to make time more accurate.
Right. And
So-
specifically, it's keeping the year, right? So we're in the exact same position we were orbiting the sun, correct?
Yes. Well, not
Ish.
quite, but in the exact same position according to the seasons.
Okay. Yeah.
Yeah, because we don't want our seasons to drift.
Right. That would be bad.
We don't want
want
to be like
Christmas
those
in the-
crazy Australians where summer comes in January.
Christmas is in the middle of summer.
Yeah. That would be, there'd be riots in the streets. I don't even know how Australia gets by. So, that was just an interesting fact I like to point out about GPS. So earlier you asked me, is the military always in contact with GPS,
Yes.
with the satellites? And yes, for the most part they are. They will contact them every day to update information about their ephemeris data and their location data. But the GPS satellites can run with low errors autonomously for 14 days and with significantly more errors autonomously for a total of 180 days.
Wow.
So even if the military doesn't
So-
contact them at all, for 180 days, they'll still operate.
So if somebody wipes out our military,
Then we still have GPS for 180 more days. So if after the initial 14 days, you'll have about 425 meter accuracy, which is not that good.
no. But it could
For-
be useful. In
For those
certain
of us
applications.
in America, that's like several football fields of distance, which is how
meter is basically
Americans
a
measure
yard.
distance
So
is football fields.
Football fields, yeah.
And after 180 days, our accuracy will be down to 10 kilometers. So you'll know what
So that's
city
like-
you're in.
So that's 6.2 miles.
You'll know basically what city you're in, and that's about
Right,
it.
Right. But you'd have a hard time hatching those 10-kilometer Pokeball.
Yeah, you'd have to
Poke
walk
eggs.
a really long
You
distance.
would know, like, if you're, or maybe not, because they'll have you jumping around, not
Yeah.
knowing exactly where
Maybe-
you are in that 10 kilometers.
Maybe that's the key to succeeding at Pokemon is
So
just
for
take out the
just-
military.
Take out the U.S. military.
So yeah, if your GPS is off by increasingly more every day, up to 10 kilometers, don't worry. That's just us getting good at Pokemon.
That's right.
But
I
no,
wanna-
in
I
all
wanna go
seriousness,
back
you
and-
should worry because that means something is wrong with the
I
Air
want to be
Force.
clear, we are not endorsing taking out the U.S. military in any form.
Cut that section.
So another interesting note about GPS, if your phone solely relied on the satellites, it would take it, if you hadn't turned on your phone in a while, if you hadn't been on maps in a while, it would need to download an almanac, and it would need to download ephemeris data from the satellites.
Okay.
And that is an excruciatingly slow process because the satellites are transmitting data at 50 bits per second.
Wow.
So
50 baud.
in case you haven't been on the internet in a while, 50 bits per second is slow.
Super slow.
Very, very slow. Those old dial-up modems, the ones that would go, welcome, you've got mail. Those old modems.
I like how you have that memorized and can reproduce it.
Man, my mom would pick up the phone and I'd be like, damn it, I almost had downloaded that song. Now I need to start over again.
The one that you paid for, of course.
Oh, of course. I never used
yes.
Napster.
Yeah.
Ever. Yeah, that would be stealing.
So now we're like, we would complain about 50 megabit per second.
That would be
So that's a million times faster
than GPS.
Yes.
So if your phone has to download all this stuff from the satellite, it can take like 10 minutes before you get a good fix. And
Wow.
if you want your fix, waiting 10 minutes for it is not ideal. You know, imagine getting in your car, you're late for a meeting and you need to find out where the meeting is, and it takes you 10 minutes before your car can, or before your phone can tell you how to get to the meeting. It'd be crazy, right?
That would be crazy.
It would be crazy.
It's crazy.
So we invented another thing called assisted GPS, which you may have seen on your phone. I don't know. They just do it nowadays. You can't turn it off in most phones. But in older phones, you could turn off assisted GPS if you were masochistic.
Why would you? Okay.
I don't
Just
know.
because you're into that sort of thing. And
I want to be late.
Yeah. So if you don't want to wait the approximately 12 and a half minutes to download an almanac and ephemeris data from your satellites, assisted GPS is great. It will just download that data from the cell tower. Nice,
okay.
huh?
That's good.
Yeah, your
So-
4G is a lot faster than satellites.
Well,
Way faster.
okay, it is. I'll give him that.
Even T-Mobile is way faster than satellites. I like T-Mobile. I shouldn't bag on T-Mobile. So assisted GPS will offload that process of downloading the ephemeris data in the almanac to some server sitting in your cell tower, basically. Will download that data and then provide it to you really quickly. Some assisted GPS can also offload position calculation to that server. I don't think that's very popular. I think your phone does all of it.
Yeah, it seems like phone processors are powerful enough now that I mean, even though it's kind of complicated math for a human to do by hand on a piece of paper, the phones could probably handle it.
Yeah, but until we update the satellites, there's no better way to get the information than just getting it from the cell tower. It's so much faster than getting it from the satellites. So the last point I want to talk about on how GPS works is how you can break GPS.
Ooh.
So this is not so much a problem for
So is that like
civilians.
hacking the planet because it's global?
Hack the planet.
In a way, sure.
Okay.
You probably couldn't jam GPS globally unless you were some really powerful military.
Like okay. They're already on to us already. We don't want to bring them up again.
But yeah, there's something called GPS jamming, where you can broadcast data on the same frequency as the GPS data, and basically cause the receivers to not be able to get a fix. So this is
Is that
the
what
biggest
they did?
problem for the military, where it can cost people's lives if that happens.
Right.
If our enemies do that. So that's why the military has this second frequency where they can broadcast encrypted information, because then the receiver can still pick it up. It knows precisely what satellite it came from. It can be absolutely sure that there's no jamming going on. I mean, it could even tell you. Like the military receivers will tell you, like, hey, there's GPS jamming going on, and they'll just start using the encrypted channels, and they'll notify you that there's jamming, and then their signal will still be fine.
Okay, to bring up politics sort of for a second, isn't that how Iran took down one of our drones by jamming the GPS signal? Do you remember that at all? It was like a few years ago. Okay,
I don't remember that.
I'll have to look that up in the next
It's
podcast.
It's plausible.
I think that's what they did, because they didn't shoot it down. Sorry, Iran, but you didn't shoot it down.
So yeah, that is how GPS works.
All right.
That was a very
So what about the naysayers? I mean, are we really on a spherical Earth?
Yes, we can be sure that we're on a spherical Earth. Well, not purposely, not perfectly spherical, but
oblate, ovoid, or something.
Oblate spheroid. Yeah. Yeah.
Words.
It's Earth shaped.
Yes.
We're on an Earth shaped Earth.
Earth shaped sphere.
We're on an Earth shaped Earth.
It's got a little extra weight in the middle, but otherwise it's pretty much the circle.
She's put on a few since her heyday. But yeah, the flat earthers, when they go out and they catch Pokemon on their phone, they're literally disproving their own hypothesis by using GPS.
Are there actually still flat earthers?
There are. There are people who literally believe that the Earth is flat.
If they get on a plane, does that?
Well, planes don't go high enough to see the curvature of the Earth.
But just go around.
Oh yeah. You could circumnavigate the Earth.
Well, they just
or you can just fly over Antarctica and see the South Pole and fly from South America.
Where's the giant waterfall on
the? Yeah, where's the edge, man? Yeah. Teach the controversy.
What happens with it?
So yeah, the flat earthers are very silly.
Okay.
They use a device every day that disproves their own hypothesis.
Unless they don't use it, because they are flat earthers.
Unless they're GPS deniers.
Yeah. GPS deniers.
It's all a conspiracy. So yeah, also relativity deniers, which there aren't many of nowadays. There used to be a lot, but nowadays pretty much everyone believes in relativity. But
or they have no
if you
idea
wanted
what
to
it
deny
is.
relativity, you could surely be persuaded by
you can
GPS.
be like the first, to be
I guess if you're denying relativity, even GPS probably wouldn't persuade you. There are so many proofs of relativity, or so much evidence for relativity. Being given GPS probably wouldn't push you over that edge. No. So yeah, GPS is great for skepticism, because it provides pretty much undeniable proof that not only is the Earth round, but relativity works. Are there any questions from our audience?
Yeah. How
is it audient? Because we have one.
No, there's multiple people here. Hey, I'm here too. I was wondering how often does the military update the satellite locations?
They'll do that about once a day.
Okay. Okay.
Pretty. Usually once a day. So every day the Air Force is updating the satellites with a new almanac and ephemeris data.
Oh,
it's that thing they do before breakfast.
Yeah.
Hey, did you update the almanac?
Oh, I forgot.
Oh, I should probably go do that. We only have 2 more weeks before we're down to 425 meters accuracy.
No.
Which is actually pretty bad.
Yeah,
it would be pretty bad for
soft.
targeted drone strikes if you were several football fields off your target.
Oh, God.
Yeah, that would be, wouldn't it?
Yeah.
And I really don't like my neighbors.
Whoops, I shot myself.
I didn't take into account relativity when I was trying to jam, and now I'm dead. So The Walking Dead, they don't have GPS currently. So maybe like late season 1 is when the U.S. government fell apart. And
certainly 180 days after the U.S. fell apart, you would no longer have any GPS.
Yeah. How do the satellites ever talk to my phone specifically? Does my phone send anything to the satellites, or it's just my phone is getting?
Okay. It's all just receiving data. The satellites don't know anything about your phone. They just broadcast their information, and your phone will receive it and use it, and never, like, your phone doesn't talk to the satellites, and the satellites don't track you or anything.
Sort of like a
GPS
podcast where we just give you information. You can't talk back to us.
That's out there.
So yeah,
Except the military contacts us periodically.
Like, the military isn't tracking you through GPS. Your GPS receiver that's why it's called a receiver.
There's a lot of people are confused about that. Like, GPS satellites do not track you.
Correct.
You track the satellites.
Yes. The satellite should be more worried about you than you should be of it.
On the other hand, the government is in your phone tracking your GPS signal all the time.
and recording.
That's right.
Also recording you.
Hopefully that is not true.
Hopefully not true.
The topic of another podcast. You mentioned that someone could jam satellites so people couldn't pick it up. Could someone jam satellites to say that Psyduck out in the parking lot is really...
Could you have a pokey jammer?
Yeah, could you have a pokey jammer?
Yeah, you could. You could totally have a pokey jammer. You can broadcast information to your phone that will tell your phone that it's in a different place that it is.
That's what I wanted to bring up.
Would be that would be a great way to cheat at Pokemon Go, is just build your own GPS satellites. Or
because that would be so feasible.
The simplest method would be to launch your own GPS satellites.
If you didn't want to walk, you could just build your own GPS satellites.
Never mind.
Or just fake your own GPS satellites, and you could trick your phone into thinking that it was somewhere else.
I have
or
read
you could
this.
just
This is a thing.
hack your phone and have it report the wrong GPS signal.
You can do that, but
that's a thing that's happening.
I know.
If Niantic, the company behind Pokemon Go, if they catch you, they will kick you off.
Yeah.
Really?
Just FYI, don't cheat at Pokemon Go because you could get kicked off.
I've read
and that'd be horrible.
That happens. Yeah, people spoof, but then their phone is telling Niantic. Like, oh, I'm cheating. Like, and
pretty much.
There was this whole thing where someone like you've got to jailbreak your iPhone, and then you like recode everything so it doesn't let them know. It's like this Pokemon arms race to try and
or you could just walk.
I can't do that.
You can just do what the game wants you to do and just walk.
Just walk around.
It's good for you.
Maybe lose some weight. I don't know.
God forbid you get outside and exercise.
I refuse. My phone, I'm sure this is a phone issue and not a satellite issue, but every once in a while, it's just...
We work in IT, but we don't fix your phones.
Fix my phone, please. So whenever I'm doing something important, like if I have an appointment to go to, my phone will say, GPS signal lost. And then I'll have to back out of the program and I'll log back in and it'll last for a while.
I think that's a phone issue with your phone. I mean,
now I'm asking you to fix my phone.
Yeah. So my phone will lose GPS signal if I have it off for a little bit, or obviously if I'm indoors, but it'll come back when it figures out what's happening. That's really important because Pokemon will tell you no GPS signal.
To be clear, though, there's more uses to GPS than just Pokemon Go.
I don't think so. I think it's
there are more, but certainly none are as important.
Right. Any other questions?
No, I had a bunch, but you answered all of them.
Oh, awesome!
All right,
that means we did a good job.
Yeah.
All right. Well, that will wrap up our first episode of Encyclopedia Podcastica.
Woo!
Woo!
We want to thank Cyber SDF for letting us use their song "Welcome" and their song "Mellow Acid" as our intro and outro music. And I hope your mind was ready, because this will all be on the test.
I hope your mind was blown with some knowledge.
But it will be on the test.
But it'll be a test.
Encyclopedia Podcastica is a production of the Silicon Valley Skeptics, an organization dedicated to promoting science and critical thinking. You can find us on Twitter at SVSkeptics or Facebook at facebook.com/svskeptics. You can contact us at svskeptics@gmail.com. If you like the show, please rate us on iTunes.